All right, we are recording.
Okay, welcome to my lecture on OpenCV. This is just going to be sort of an overview of some different techniques you can use in OpenCV to solve an image processing task. And the way this is going to work, I'm going to go over a problem that we had to solve 2 years ago in MATE ROV, and basically how we went about doing it. So to start, we're going to be doing this in Python, and there's going to be some libraries you need to install. So if you do want to try and running this code yourself, just use pip install and install these libraries, and then use these import statements. So the task we're trying to solve here is basically determining the length of this blue rectangle. And what we're given is that it's 2 centimeters in width, and we have grid lines that are 30 centimeters apart. So just from a single image, we want to be able to tell what the length is in centimeters. So obviously, we're going to need to isolate this area, the blue rectangle, from the rest of the image. And what's nice about this is it's pretty easy to do based on the color. As you can see in this image, there's only one region of blue, and it's fairly distinct from the other colors of basically red, white, and black in this image. So what we're going to use is a color mask, and basically a mask is just sorting pixels on and off within an image, and we want to choose the pixels that are within a certain range of color values. So we're going to try and find a range of blue values that isolates that blue rectangle. So there's different ways we can represent colors. So usually they're stored in an RGB. That's what everyone's most familiar with, red, green, and blue. And those 3 values range from 0 to 255. But it's not always straightforward using RGB to determine exactly what values. Because, okay, obviously we want a high level of blue, but how much green and red, it can be a little hard to sort of reason through that. And it can be a lot easier to use different color spaces, we can use HSV or HSL. So both of these use hue and saturation, and then either value or lightness. So I'm going to go over about the differences between these two. So in both these color systems, hue is represented the same exact way. If you convert into HSV or HSL, the hue is always going to be the same. And it's the saturation and value and lightness that differ slightly. So on the right, you can see it's sort of like a representation of the coordinate system, sort of like a polar coordinate system you're using here. And the difference here is really at the top of the values, like high values can be, pure colors or white. Or if you see an HSL, a high lightness value means basically the color is white. And then the saturation, if you have a high saturation in HSV, it's not white, but a high saturation in HSL could have some white or very close to white. So it really depends on the situation which one you want to use here and how you're trying to differentiate colors. So in this specific case, I would say HSV would probably be better because we want to differentiate between blue and white. So in HSL, it's a little bit harder to do because with HSV, we can just say we want a high saturation, and that'll pretty much get rid of most of the white values, where the high saturation in HSL could still get us those white values. So what we're going to do is look at the hue values and choose ones that are actually blue. So really you can use an image editor and use a color picker and to try to determine your hue values. And then we'll want obviously a high saturation value because it is like a blue color, it's not gray or white. And then the value is one we want to sort of allow for a large range for, because we don't really know what the lighting conditions are, and especially with ROV underwater, it can get kind of dark, and so the lighting being so ill-defined, we want to allow for a large value, which we can in the HSV color space. So here's like the actual code you would use to create this color mask. So here we have a method called mask blue. So the first line there is we're converting from BGR to HSV. A weird quirk with OpenCV is it doesn't use RGB, it uses BGR. So for some reason they put the blue first instead of red, but that doesn't really matter too much because we're converting to HSV anyway. So you can use this convert color method to convert your image into HSV. And so then you'll want to define your lower and upper ranges for each hue, saturation, and value. So in CV, our hue values will range from 0 to 180, and then saturation and value ranges from 0 to 255. So these are the values I chose, which produced the image on that right. So that seemed to work pretty well, and really is this sort of like trial and error, and obviously using a color picker tool to actually see what those colors are to make sure you're getting it within that range. So then this CV2.inRange function is just going to go through each pixel in that image and check each of the 3 channels in that image and make sure they're within the ranges for all 3. And if so, it'll make it white, and if not, it'll make it black. So here we just have like a binary image of just white and black, whether it's in the range or not, and it does isolate the blue rectangle pretty well. And then here's the, you can see the code I used to actually run it. So we can use this imread to actually read in a file and store it in a variable. And then I create the mask. And then in my code, I use a helper method called, or we have this helper method from imutils called resize that'll resize it for us to actually show it. So then to actually see what you've done with OpenCV, you can use this imshow method, and you give it a string as a title. That's just the title of the window, and then the actual image you want to display. And then what you want to do is use this wait key method, and that just tells OpenCV to wait until the user presses a key. Because otherwise, if you just ran this code without the wait key, it would terminate, and you can since it reached the end of the file, and then it would close out all your windows. So you want that wait key so you can actually see what happened, and then once you hit the key, everything will exit out. Yeah, so imread and imshow are very helpful for testing your code with different images and seeing what's happening in the intermediate steps as you're trying to find your answer. So next we need to use a concept called contours in OpenCV, and I just copied this definition from their documentation. So it's just a curve joining continuous points of the same color, basically. So in this case, we want to find the contour or the shape of this rectangle from the mask. So it works well with binary images where there's only essentially 2 colors. So we can find those boundaries pretty well. So the method you use is called findContours. And what it does is it takes 3 parameters, your input image, and then 2 others, contour retrieval mode and the approximation method. So I linked to some websites on the documentation about to go into more detail about what these will do. But the contour retrieval mode tells it how to handle nested contours, and it can build like a sort of a hierarchy of which contours are inside others. But in our case, we don't really need to do that. We only expect like 1 contour without any nested because there shouldn't be any other blue areas. So what we'll do for the contour retrieval mode is just what's called like the external mode, where it just gets the outermost, since we don't really want any sort of nested contours. And then the approximation method is just how it simplifies the shape. So we don't necessarily want every single pixel on the boundary. We can simplify it and still get basically a good result. So here's that in code. We use the findContours, and the retrieval mode is the external, so we only get the outermost contours. And then this, the approximation, we use a simple approximation, and that's not really going to change much, but you can look at the documentation to read more about that. And then the rationale here is we want to find the contour with the maximum area, which we can find with the contour area method. So obviously there might be some noise in the image and there might be some random regions of blue where we don't really expect them, but those shouldn't be too large. So in most cases, we'll only get one contour, but if we do, we'll just take the one with the largest area. And from there, we're almost to our answer. We have this method called min area rect, which just finds the minimum rectangle that encompasses a contour. And so that gives you the coordinates where I think the top left corner is, the width and the height, and then the angle. So it can handle diagonal rectangles if you need it to. And so once we have the width and the height, basically we can use a ratio between the width and the height. And then since we know our width has to be 2 centimeters, multiply that ratio to get the length. So this works pretty well. But we do also have the grid lines here. So we could also use those to measure our length of the rectangle. And this method, the ratio method, doesn't really account for any sort of perspective. Now the images we're looking at are pretty straight on, but if there's any sort of angle to how we're viewing the plane, it's going to mess up the ratio and might give us some bad results. So we can correct for the perspective here. And what we would need to do for that is isolate the grid lines from the image, and then find those intersection points. So we have a square, and since we know like that quadrilateral we have in the image has to be a perfect square, we can create a transformation that OpenCV will do for us, and transform that image into a perfect square, and then compare the length of the rectangle using the same color mask, and to compare it to the length of that square, which we know is 30 centimeters. So based on testing with actual footage from underwater, we found the color masking did not actually work too well for finding the grid lines. And part of that is because we had a light on the robot that was shining on our plane, and it was creating some more lighting in the center than on the edges. So there's different lightness to the grid lines. So one way you can sort of get around that, if you don't really have a constant color or constant lightness to your image, you can use adaptive thresholding, which OpenCV has, which I linked to if you want more information on that. But basically it's looking at each pixel and then looking at all the pixels in its immediate neighborhood. And if it's significantly darker or lighter, then basically we turn that pixel on to create a mask. So first, to actually do the adaptive thresholding, you need to convert it into gray so it only has one value for the color instead of 3. So then you plug it into the adaptive threshold method. And you can look into the documentation on what exactly all these parameters do. But you can adjust how big the neighborhood is and basically what level your threshold has to cross to turn on the pixel in the mask. So if you do this adaptive threshold on that image, you can see it isolates the grid lines pretty well. But the problem here is we have still all the grid lines from the red tape and the blue tape. So we want the grid lines, but we don't want the edges to those red and blue regions. So what we can do is we have a mask for the blue region already, all we really need to do is create another mask for the red region, and then we can sort of combine all of these masks into one mask where it's just the grid lines. And what we'll want to do for the red and the blue regions is the adaptive threshold still finds like some pixels immediately outside the areas of red and blue. So what we'll do is use a method called erode, which basically just expands a mask by a certain amount so that we can make sure we get all the regions around the blue and the red. So here's that implementation for isolating the grid lines. So first we make a mask for the red. So we convert to HSV, make a range and use the in range. Make a mask for the blue. And then CV has this bitwise method, so we can bitwise OR to combine the red and the blue mask, and then bitwise not because we want the areas outside of blue and red. And then we'll use the erode method to make that mask just a little bit bigger to make sure we definitely exclude all the areas around the blue and the red. And then it can be helpful to use a blur before you do the adaptive threshold because usually there is some noise and then you can get some random pixels in the middle that show up on the adaptive threshold, but the blurring can help mitigate that. So once we have our threshold, we use this bitwise and with our eroded mask from before to exclude all those areas. And on the right, you can see what image we actually get. So it seems to isolate the grid lines pretty well. You'll notice some of them sort of cut out, but as long as we have most of it, it should be good. And then one thing to keep in mind, weird quirk with HSV color space is when you're masking for red, you can have values close to 0 or values close to 180. So sometimes you might need to use 2 masks basically to fully get all the red in that, but at least in this image that I was testing on, they didn't cross over to 180. So now that we have our grid lines, what we'll need to do is actually find like the coordinates of those straight lines. So I linked to one way you can do that in OpenCV, and this lines transform returns lines in polar coordinates. So what it'll do, it'll give you the radius away from the origin and a theta value, and that tells you that theta is really what sort of perpendicular to that line. So you can express any infinite line in 2D space with these 2 coordinates. So here's that implementation. So first we use our grid line mask to get a mask. And then I created this show resize, this helper method to call the imshow and the weight key. I'll put a link to this code in full so you can see all the helper methods I use, but basically that's just showing the image for debugging purposes. And then we use the hoe lines to find all the locations of the lines from that grid line mask. And so there is this parameter line thresh that needs to be adjusted. It basically says how sensitive it should be to lines. So if you make that too low, you'll get some false positives, but if you make that too high, you might miss some of your grid lines. So a lot of this is trial and error based on testing images and finding which parameters work best for you. So on the right, you can see what this actually returns. I drew the lines on the image just to visualize it. And you can see it returns a lot of lines, a lot of separate lines for each individual grid line. So it will take some more processing to actually find like where these intersection points are. Yeah, so unfortunately I didn't get time to really go into too much detail here. But if you have any questions, you can message me on Slack if you need more clarification on what's going on here. But basically, so we have these lines, and each line is just an array of 2 coordinates, the radius and the theta value. And so what we do here is sort the lines into the vertical and horizontal, and we can do that just based on the theta value. And the theta just ranges from 0 to pi. So we can look for lines that are close to 0 or close to pi and put those in our vertical list. And then we also look for lines that are close to pi over 2, which would be our horizontal lines. And so then we created a method called cluster that takes those lines and sort of clusters them into 2 groups, because we'll have, from the vertical lines, we'll have the left ones and the right ones, and for the horizontal lines, we'll have the bottom grid lines and the top grid lines. So if we want to cluster things, we can use what's called k-means clustering. And you can look up exactly like what's going on internally, but the idea is you're just giving it like a list of numbers or coordinates, and so you can have like 1 or 2 or 3 dimensional coordinates if you want, but in this case we're just giving it the radiuses or radii and telling it to find 2 clusters, and then we take those 2 clusters and sort them into 2 lists. So that's what the cluster method is doing. So we take the vertical lines and the horizontal lines and get 2 clusters from each of those. And then from each of those clusters, we find the intersection between them. So I created a helper method called intersect that takes each cluster. And what that is doing is it's finding the intersection between each pair of lines in those clusters, and then finding the average coordinate from that. So I didn't actually include that in the presentation because it's really just algebra, but you can see that in the full code if you want to see how that is calculated. So from this, we should have our 4 coordinates of where our grid lines intersect. So what we can do now is actually figure out how to create a perspective transform. So here we define some constants. So the image size is just how many pixels we're going to make our warped image. So I just chose 3000. This doesn't really matter too much. I just was trying to make it big enough so we don't like lose detail when it resizes it. And then the scale is the number of centimeters per pixel. So we know the grid lines are 30 centimeters apart. So we just do that division and use that for calculating lengths. So the get perspective transform method in OpenCV will give us a matrix that transforms from our original image into a warped image, where we're making the square or whatever quadrilateral we found into a perfect square. So the intersections is just the list of 4 intersection points we have. So that's our source list of coordinates, and then we define this destination, which is just a square of 3000 pixels on each side. So then you use this warp perspective to take our original image and create a warped image. And so then on the right, you see this is what the warped image looks like. So you can see we've pretty much cut out the grid square and warped it slightly so it's actually perfectly square instead of a little off based on our perspective. And so from this, we just use the same technique as earlier. We use a blue color mask and find the largest contour. And so then we can get the width and the height from that using this helper method from using the same technique as before. And then we just choose the largest dimension, since we didn't know if it was going to be vertical or horizontal. It could have been either. So you just choose the largest dimension and use our scale factor to actually find its length in centimeters. And so that's it, basically. Yeah, so I was just hoping to sort of do an overview of how you go about solving problems here. So a lot of working with OpenCV is reading documentation. So if you're curious on how things are working here, definitely look through the links I put on this slide, and so you can get a better idea of what's actually going on under the hood. yes, thanks for watching.